Good morning. Today we're going over our last assignment on chapter 6, which is stoichiometry, and we've only got like 10 problems in here, but they're all a little bit long and involved because we've got a lot of dimensional analysis. So it might take you a little bit of time, still probably about half an hour to 45 minutes, but I hope this video will help. Let's get started. In the first case, we're looking at the relationship of moles of reactants to moles of products, or essentially we're looking at the coefficients in here to determine mole-to-mole ratios. So for instance, I can see, according to this reaction as given, 1 mole of carbon dioxide reacts with 4 moles of H2 to produce 1 mole of CH4 and 2 moles of H2O. So the question is, how many moles of methane, that is CH4, are produced when 25.1 moles of carbon dioxide gas, that's this, CO2, react with excess hydrogen gas? They're telling us we've got enough hydrogen gas to make this work. So if I go over here, I can say I'm given, we have 25.1 moles of CO2, and they want to know how many moles of methane, CH4. So anytime you're going back and forth between moles of different things, then you're going to be using the coefficients here of the balanced equation, and the coefficient between CO2 and CH4 is 1 to 1. It appears to me, according to this equation as written, that 1 CO2 is equal to 1 CH4. For the purposes of this equation only, those two things are equivalent, because if I've got one of these, I can make one of those. So if I've got 25.1 moles of CO2, then I'm going to have 25.1 moles of CH4. The way I do this mathematically is I start with what I was given, 25.1 moles of CO2, and I multiply that by 1 mole of CH4 for every 1 mole of CO2 from this equivalency when CO2 is equal to 1 CH4. So my moles of CO2 cancels, and I get moles of CH4, which is what I was asking for. And if I do 25.1 times 1 divided by 1, I'm going to get 25.1 as my answer. Next, it asks how many moles of carbon dioxide gas would be needed to react with excess carbon dioxide to produce 76.6 moles of water vapor. So our goal is 76.6 moles of water, H2O, and they want to know how many moles of H2 gas did I start with to get me there. So if I look at my equation again, I see that 4H2 goes to form 2 H2Os under these conditions. So for the purposes of this equation, 4 moles of H2 are equal to 2 moles of H2O. So if I plug this in dimensional analysis, 76.6 moles of water divided by 2 moles of water for every 4 moles of H2, then my moles of water cancel, and I'm left with moles of H2, which is what they asked for. So if I plug this into the calculator, 76.6 times 4 divided by 2, and I get 153.2 moles, just like that. So now we're given some equations, and they're asking me what conversion factors I'm going to use. And for instance here, for part A, 2 SO2s plus 1 O2 goes to form 2 SO3s. They want to know what conversion factor I would use to go back and forth between SO2 and O2. And that's just these first two, right? So I could ignore SO3 for the moment because they're not asking about it. It's still there. We're just not asked about it. So 2 SO2s and 1 O2. So 2 SO2 equals 1 O2. So 2 SO2 on the top, 1 mole O2 on the bottom. That's fine. And we could also flip it and put 2 SO2 on the bottom and 1 O2 on the top. That is perfect. In this case, I've got the wrong number of moles attached to my O2 and my SO2. And same thing with the bottom here. Next, what's the relationship between SO2 and SO3? SO2 is 2 and SO3 is 2. So 2 SO2 is equal to 2 SO3. So we need the one that's got 2 moles of SO2 on top, 2 moles of SO3 on the bottom, and the other one that has the 2 moles of SO2 on the bottom and 2 moles of SO3 on the top. Those would be the two conversion factors we could use. And for part C, they're asking about O2 and SO3. We see that 1 O2 goes to form 2 SO3. So 1 O2 forms 2 moles of SO3. So this bottom option that I've got has 1 mole of O2 on top, 2 moles of SO3 in the bottom, and then 2 moles of SO3 on the top, 1 mole of O2 on the bottom. So that's the right one. Now parts D, E, and F is doing the same thing, but now we're looking at the equation of 4 phosphorus plus 5 O2 goes to form 2 P2O5. So the relationship between P and O2 is this 4P and 5 O2. So 4P and 5 O2. It looks like the second option, which has 4 moles of P divided by 5 moles of O2, and 5 moles of O2 divided by 4 moles of P is the right answer. Next, between P and P2O5, we have 4 P's, 2 P2O5s. So 4 P's, 4 moles of P divided by 2 moles of P2O5, and 2 moles of P2O5 divided by 4 moles of P. That's what we're looking for. And finally, the relationship between O2 and P2O5, we have 5 O2s and 2 P2O5s. So 5 moles of O2 divided by 2 moles of P2O5, and 2 moles of P2O5 divided by 5 moles of O2 would be the 2 conversion factors that we would use to solve that problem. Problem 6.47, we're going to actually plug this in, and we're going to do it exactly like we did in the first problem. So what we're going to do is start with my equation here. We have 2H2 plus O2 goes to form 2H2O. And this is going to tell us that 2 H2s react with 1 O2, and vice versa. 2 H2s produce 2 H2Os, and vice versa. And 1 O2 produces 2 H2Os, and vice versa. So if they want to know how many moles of O2 are required to react with 4 moles of H2, we're looking at this relationship. And if I have 4 moles of H2, we know that 2 moles of H2 reacts with 1 mole of O2, so I'm going to put the 2 moles of H2 on the bottom and the 1 mole of O2 on the top so that my moles of H2 will cancel, and that tells me 4 times 1 divided by 2 should give me 2 moles of O2 that will also react. Next, part B, if I have 9 moles of O2, how many moles of H2 are needed for the reaction? So 9 moles of O2. And they want to know H2. So if I'm starting with O2, then again, I'm going to use the same conversion factor I used for part A, where 1 mole of O2 reacts with 2 moles of H2. But now I'm just going to flip that conversion factor so I can cancel out moles of O2. And that gives me 9 times 2 should give me 18 moles of H2 will also react if I have 9 moles of O2. Finally, how many moles of H2O form when 6.5 moles of O2 reacts? If I have 6.5 moles of O2, and I need to know how much H2O I get, I can see, according to my equation as written, that 1 mole of O2 goes to form 2 moles of H2O within this reaction. So 1 mole of O2 I'm going to put on the bottom so that I can cancel those units, and 2 moles of H2O on top, so I can get the units that I need, and 6.5 times 2 should be 13 moles of H2O. In the reaction shown, how many moles of HCl are needed to react with 2.4 moles of Al? So we start with 2.4 moles of Al, which is given, and the reaction they give us says 2Al plus 6 HCl goes to form 2AlCl3 plus 3H2. But they only want to know how much HCl given a certain amount of Al. So we could ignore the products and just look at the first two that says that 2 Als react with 6 HCls. So 2 Als on the bottom, 6 HCl on the top. My Als cancel, and I get 2.4 divided by 2 times 6, 7.2 moles of HCl. Of course, your numbers might be different than mine. It's very common for mastering chemistry to randomize the number variables. Okay, so next we're looking at mass relationships, which is going to be exactly the same. except that now we're going to plug in our molar mass to our equation. Dimensional analysis. So we know molar mass of butane, C4H10, has 4 carbon atoms and 10 hydrogen atoms. We know, according to the periodic table, that carbon has a mass of 12.011 and hydrogen has a mass of 1.0079. So the molar mass of C4H10 is 58.12 grams per mole. We've already done that a bit in our last homework assignment. So next they want to know what mass of water would be produced if 8.32 grams of butane reacts with excess oxygen. So we've got this equation here that says 2C4H10 plus 13O2 goes to form 10H2O and 8CO2. So if I start with 8.32 grams of butane, that is C4H10. And I want to get to something else, in this case, water. As we just saw in the first 4 problems, we need to use mole-to-mole relationships. And I can see that 2 moles of C4H10 goes to form 10 moles of water. But I don't have moles of C4H10, I have grams. So what I'm going to do is use the molar mass that I just calculated here to convert between grams and moles, because I just calculated that it takes 58.12 grams of C4H10 to make 1 mole of C4H10. So my grams of C4H10 will cancel, and now I have moles of C4H10, so I can do what I've been doing for the last few problems, which is to say that for every 2 moles of C4H10, I can produce 10 moles of H2O, according to this equation as written. So now my units of moles C4H10 cancel, and I have moles of H2O. Awesome. But they didn't want moles of H2O, they want grams of H2O. So to get to grams of H2O, I'm going to need the molar mass of the water. So water has 1 hydrogen, 2 hydrogens at 1.0079, and 1 oxygen at 15.9994, and that gives me 8.0152 grams per mole, or 8.02 grams per mole. And I'm going to put the 18.02 grams water for every 1 mole of water, and I'm going to put moles of water on the bottom, this dimensional analysis line, so that will cancel out my moles of water, and I'll be left with my answer in grams of H2O. So that is 8.32 grams C4H10 divided by a molar mass of 58.12 grams of 58.12 grams of C4H10 per mole of C4H10, multiplied by 10 moles of water divided by 2 moles of C4H10, and then finally multiplied by 18.02 grams of water in a mole. And I should get 12.90 grams. Perfect. We're going to do the same thing, except for now we are given the mass of carbon dioxide, and we have to go back to find the mass of butane that we started with. So if we start with mass of carbon dioxide, 51.2 grams CO2, and I know I can get from carbon dioxide to methane using moles, because clearly 2 moles of methane makes 8 moles of carbon dioxide, but I'm not given moles, I'm given grams. So I have to go from grams to moles, and that means you need the molar mass of carbon dioxide, 1 carbon, 12.011, plus 2 oxygens at 15.9994, gives me a mass of 44.01 grams per mole, 44.01 grams CO2 in every 1 mole of CO2. If I put grams of CO2 in the bottom, then those will cancel. And now I can look at my equation and see 8 CO2s were made from 2 C4H10s. 8 moles CO2, I'll put that on the bottom. 2 mole C4H10. I'll put that on the top, so my moles of CO2 will cancel. And then finally, because they want mass of butane, that means units of grams. In fact, you can see units of grams right there. We're going to put in our molar mass of 58.12 grams of C4H10. And every 1 mole of C4H10, moles of C4H10 cancel, we should get our unit answer in grams of C4H10. So that's 51.2 grams of CO2 divided by 44.01 grams of CO2 in a mole, multiplied by 2 C4H10s for every 8 moles of CO2, so divide by 8, and then multiply that by 58.12 grams of C4H10 per mole, and I get a mass of 16.9 grams of butane. That's it. Now, this might feel a little bit involved, but note that what I've done here are 2 molar mass conversions, which you guys are really good at. You did on your last homework assignment, and 1 mole to mole conversion we've got right here. These aren't hard. You guys know how to do these. The hard part is remembering which conversion to do when, because you know how to do each of these conversions. So what I give you on the exam is what I call the conversions roadmap. So let me bring that up here. All right, so I have loaded up the conversions roadmap for you here, and hopefully you can see this is something that you get on the exam support material. So when you go in to take the exam, you're getting this whole sheet of paper, and it's got these equations and this table of electronegativity values, but really you just need right now, we're going to pay attention to this conversions roadmap. So at first it might look a little bit complicated, but honestly, this is everything we've been doing, and it just tells you when to do what. So if you learn how to use this, this is going to help you immensely on the homework, I promise. So please just take a minute and look at this with me. I've got only 2 things going on here, and they're repeated. So I have A, that's referring to one thing, which I'm calling A, but it could be any one thing. And then B, that's referring to a different thing, B. And so A is different from B, but A could be anything and B could be anything. So you see, the only way to get from one thing to something different is to go through the mole to mole ratio using the coefficients of the balanced equation. If I have moles of any one thing, then I can find grams of that using its molar mass. And if I have moles of something different, moles of B, I can get to grams of B using its molar mass of B right there. And then, of course, if I use Avogadro's number, I can get to particles of that any one thing. So here in part A, let's use this with our question here. Problem 6.55, part A. How many grams of H2O are required to react with 31 grams of NO2? So we want to know grams of something, in this case water, and they're giving us grams of something else, in this case NO2. So something and something else is A and B. And it doesn't matter which one I say is A, which one I say is B, but they're giving me grams of one thing. I'll call NO2 A. They're giving me grams of A. And they're asking for grams of something else. So something else has to be B. So they want grams of B. So I'm starting here on my roadmap at grams of A. And I want to get to here on my roadmap to grams of B. Awesome. Then I can use the roadmap to tell me how to get there. And the roadmap says use the molar mass of A to get to moles of A. Then use the coefficients of the balanced equation to get to moles of B, and then use the molar mass of B to get to grams of B. So that's what we're going to be doing. So we come here and we see, according to our roadmap, starting from grams of A, we want to go to moles of A using the molar mass of A. So if A is NO2, 31 grams of NO2, we want to get moles using molar mass. 1 mole of NO2 has certain number of grams. We're going to have to calculate that using the masses on our periodic table. We've got 14.01 for nitrogen plus 2 times 15.9994 for oxygen. So we get a molar mass of 46.01 grams of NO2 for every mole. And then, according to our conversions roadmap, once we're at moles of A, we've used the molar mass, we get to moles of B by using the coefficients of the balanced equation. Great. We need H2O and NO2, and we see from the balanced equation that 3 moles of NO2 react with 1 mole of H2O. So 3 moles of NO2 with 1 mole of H2O. And I've set these conversion factors up so that the units cancel. Now I'm at moles of H2O, and we said that H2O was B, so we're at moles of B. I need to get grams of B because that's what they asked for. So I'm going to use the molar mass of B, and we determined actually previously that the molar mass of water is 18.02 grams in a mole. Grams of H2O, 1 mole H2O, so those cancel, and now we can just plug those numbers into our calculator. So 31 grams of NO2 divided by 46.01 grams of NO2 in a mole, divided by 3 moles of NO2 in a mole of water, and multiply that by 18.02 grams of water in a mole of water, and we get 4.05 grams of water. Next, how many grams of NO are obtained from 15.3 grams of NO2? We're going to do the same thing. Our roadmap says if I'm given grams of one thing, in this case NO2, and they want grams of something else, in this case NO, one thing and something else are A and B, we're going to go through the conversions roadmap. So starting at grams of A, which is NO2, I'm going to use the molar mass of NO2 to find the moles of NO2. And then once I'm there, I could use the coefficients of the balanced equation between NO and NO2, which says that 3 moles of NO2 reacts to form 1 mole of NO. That's going to get me to moles of B. And finally, I can use the molar mass of B, which is NO, to get to grams of B. So that's how the conversion roadmap is going to help me get from where I am to where I want to be. So starting with 15.3 grams NO2. And I already have the molar mass of NO2. I figured that out on the last question. And then once we have moles of NO2, we can look at the equation and remember that 3 moles of NO2 makes 1 mole of NO. And finally, we find the mass of NO is about 30 grams per mole. And we plug this into our calculator. We have 15.3 grams NO2 divided by 46.01 grams of NO2 in a mole, divided by 3 moles of NO2 and 1 mole of NO. Multiply that by 30 grams of NO and a mole of NO, and I get a total mass of 3.33 grams of NO. Finally, how many grams of HNO3 are produced from 8.3 grams of NO2? We're going to do exactly the same thing because they're giving us grams of one thing, NO2, and they're asking for grams of something else, HNO3. So if we follow the roadmap says if we start with grams of A, in this case grams of NO2, we're going to use the molar mass of A to get us to moles of A, and we calculated previously the molar mass of NO2 is 46.01 grams. Next we use the mole ratio. We have got 3 moles of NO2 makes 2 moles of HNO3. So 3 moles of NO2 on the bottom, 2 moles of HNO3 on the top. So my moles of NO2 cancel. And then finally, I need the molar mass of HNO3, H 1.0079, nitrogen 14.01, 3 oxygens at 15.9994, and I get 63.02 grams per mole of HNO3. And now I plug this in. 8.3 grams of NO2 divided by 46.01 grams of NO2 in a mole, multiplied by 2 moles of HNO3 divided by 3 moles of NO2, multiplied by 63.02 grams of HNO3 in a mole, and I get a total mass of 7.58 grams of HNO3. All right, so this next problem just continues what we've already been doing, but kind of looking from a broader perspective, like why do we care about this kind of a thing? And we're looking specifically at Tamiflu. Tamiflu is an antiviral drug, and they've got a lovely picture here of the tablets, and this shows the star anise that it comes from. And this is the shikimic acid, which is the starting material which is extracted from the star anise, which is then used to make Tamiflu. So the first question they have here, what is the formula of shikimic acid? And they tell us the black spheres are carbon, the white spheres are hydrogen, the red spheres are oxygen. And figure 3 here shows this three-dimensional image of shikimic acid. And if we look carefully, I think you'll see we count 7 carbon atoms, that is 7 black spheres, and 10 hydrogen atoms, that is 10 white spheres, and 5 oxygen atoms, that is 5 red spheres. So that's going to be C7H10O5. Next, what is the molar mass? And we know how to calculate the molar mass. That's easy. We just take the number of each types of atoms and we multiply that by the mass of each one and we add it up. So 7 carbons at 12.011 grams per mole, plus 10 hydrogen atoms at 1.0079 grams per mole, plus 5 oxygen atoms at 15.9994 grams per mole, and I get a mass of 174 grams per mole. I always use all of the digits when I'm adding it up, but then in the end I round down. In this case, they say specifically they just want 3 digits, so that's what I'm giving them, 174. Now they want to know how many moles of shikimic acid are contained in 150 grams of shikimic acid. So this is just a gram to mole conversion. So if I have 150 grams shikimic acid, and we just determined that there are 174 grams in a mole of shikimic acid, 174 grams of shikimic acid in 1 mole of shikimic acid. I'm going to set that up so that 174 is on the denominator so I can cancel out grams of shikimic acid. And then I plug that into the calculator and see 150 divided by 174 gives me 0.862 moles. 0.86, they only want 2 significant digits. Next, how many capsules containing 75 milligrams of Tamiflu could be produced from 146 grams of star anise? Well, they give us up here, from 2.6 grams of star anise, I can get 0.13 grams of shikimic acid. And that is used to produce 1 capsule containing 75 milligrams of Tamiflu. So every 2.6 grams of star anise will produce 75 milligrams of Tamiflu. That is 1 capsule. For the purposes of this industrial process, we see 2.6 grams star anise is used to produce, or is equivalent to, 0.13 grams of shikimic acid. And that is used to produce, or is equivalent to, 75 milligrams of Tamiflu. And that represents 1 capsule Tamiflu. So if we have 146 grams star anise, they want to know how many capsules, which each contain 75 milligrams of Tamiflu. We see that 2.6 grams of the star anise can be used to produce 1 capsule. Cancel our grams of star anise. We set that up, 146 divided by 2.6. We get 56.15 capsules, or 56 capsules. What is the molar mass of Tamiflu? Now we're referring to this formula up here, C16H28N2O4. We're just going to plug it in. 16 carbon atoms times 12.011 grams per mole for each carbon atom, plus 28 hydrogen atoms multiplied by 1.0079 grams per mole for each hydrogen atom, plus 2 nitrogen atoms at 14.01 grams per mole for each nitrogen atom, plus 4 oxygen atoms at 15.9994 grams per mole for each oxygen atom, and I get a total of 312 grams per mole for Tamiflu. Finally, how many kilograms of Tamiflu would be needed to treat all the people in a city with a population of 400,000 if each person takes 2 Tamiflu capsules a day for 5 days? So first of all, let's say we have 400,000 people and they each have to take 2 capsules a day. 2 capsules a day. And they have to do that for 5 days. So we set that up 400,000 people times 2 capsules per day times 5 days, days cancel, and we determine how many capsules we're going to need for that many people. So 400,000 times 2 times 5, and that gives me 4 million capsules. 4 million capsules to treat that population. Now they want to know how many kilograms of Tamiflu, and we just saw that every 1 capsule contains 75 milligrams of Tamiflu. 1 capsule, 75 milligrams of Tamiflu. I'm putting the capsule on the bottom, so those will cancel. So 4 million capsules multiplied by 75 milligrams per capsule, but they wanted kilograms, not milligrams. So we have to remember that there are 1,000 milligrams in 1 gram. That takes me to grams. And that there are 1,000 grams in 1 kilogram. If I set that up thusly, then I will get units of kilograms, which I want. So we have 4 million capsules multiplied by 75 milligrams of Tamiflu per capsule, divided by 1,000 milligrams in every gram, and divided by 1,000 grams in a kilogram, and that gives me 300 kilograms of Tamiflu that would be required to treat that one city with a small population of 400,000. For this next question, they want to know the mass of CO2 that can be produced by the reaction of 49 grams of propane if you have a 59% yield. So percent yield is not that difficult. In fact, this is something that you do every single time you do an assignment or you take a test. It's exactly what you would expect. There's a little formula that this is going to make sense. And I think this will make sense once you see it. Your percent yield is the actual yield, what you actually got when you measured it in the lab, divided by your theoretical yield. This is what you theoretically could have gotten according to your mathematical calculations. And then you multiply, that just gives you a fraction. And then you multiply it by 100 to make it a percent. So when you go to take a test, theoretically, you could get 25 questions right. You actually got 20 of the 25 questions right. So your grade is 20 divided by 25, which ends up being 0.8, but we are accustomed to multiplying it by 100 to make that a percentage, and then you could say I got 80% on that test. It's exactly the same thing. Your theoretical then is what you calculate, like this is what you could possibly get. You can't get any more than that based on what you started with. And then the actual is what you measured in the lab based on the performance of the reaction itself or the performance of the reaction or your performance in the lab. You might get lower results. So that's what's going on here. And you can use this formula, but hopefully you'll remember it really is just like calculating your grade. And you have done this many times. So let's look at this. We have C3H8 plus 5O2. This is a balanced equation. Goes to form 3CO2 plus 4H2O. And they're saying calculate the mass of CO2. They want grams of CO2 that can be produced if the reaction of 49 grams of propane, that's the C3H8, 49 grams of propane, and sufficient oxygen. They're just saying don't worry about how much oxygen you've got enough to make this work. And the 49 grams of C3H8 produces how much carbon dioxide, and they're telling you also that this reaction is typically going to give me 59% yield. So I'm going to calculate how much I could get and then say I'm really only going to get 59% of that because this reaction is not being particularly efficient. So if we look at our roadmap, just like we've been doing, we see that we're going from grams of A. We're going to say that C3H8 is A. And we want grams of something different, so we're going to call that B. So we're going grams of A to grams of B. And if you look at your roadmap, it tells you what to do. You know how to do all these conversions, but it's helpful for it to tell you which one to use first. So the first one they say is use the molar mass of A to calculate the number of moles of A. So if I have 49 grams of C3H8
Then I need the molar mass of C3H8, and that's going to be 3 times 12.011 plus 8 times 1.079. I get a molar mass of 44.0962 grams per mole. I'm just going to round that to 44.1. 44.1 grams of C3H8 in every 1 mole of C3H8. So this is all, you've done this before. Your grams of C3H8 cancel. And then next, the roadmap says once you have moles of A, your next step is to find moles of B by using the coefficients of the balanced equation. And those are 1 for the C3H8 and 3 for the CO2. So I'm going to put 3 CO2 in the numerator and 1 C3H8 in the denominator. I should say that's 3 moles of CO2 and 1 mole of C3H8. So moles of C3H8 cancel. And then next we need the grams of B, and our roadmap tells me that if I have moles of B and I want grams of B, I need to use the molar mass. So that's going to be 1 carbon at 12.011 plus 2 oxygens at 15.9994. Gives me a molar mass of 44 grams in a mole. And that gives me grams of CO2 produced. So 49 grams of C3H8 divided by 44.1 grams of C3H8 in a mole of C3H8 multiplied by 3 moles of CO2 in every 1 mole of C3H8, and then multiplied by 44 grams of CO2 in a mole of CO2 gives me a theoretical yield of 146.7 grams of CO2. That is the most I could possibly get from this starting material, right? Because I can't make carbon atoms out of nothing. So all the carbon atoms in CO2 came from my C3H8. If I start with 49 grams of C3H8, the most I can possibly get of CO2 is 146.7 grams. Now, again, here, this tells me I only get 59% yield. So if this is my theoretical and they want the actual yield, they're saying how much can be produced, then I can rearrange this equation. I'm going to multiply both sides by the theoretical yield, then divide both sides by 100 to get the actual yield. So percent yield is 59. Multiply that by 146.7, that's the theoretical yield. Divide by the 100, that made it a percent, and we see that we actually get 86.6 grams. So this is the exact same type of problem, exact same type of question, but instead of giving you the percentage and ask what the actual one was, they're giving us the actual and they're asking us what the percent is. But otherwise it's the same. We are given an equation Fe2O3 plus 3CO goes to form 2Fe plus 3CO2. And they're telling us that we have 50.0 grams of iron 3 oxide. That's the Fe2O3. And they want to know what the percentage yield is if I only get 32.7 grams of iron, that is Fe, in the product. So we're going to take the 50.0 grams and then calculate the theoretical. And then we could apply the actual versus the theoretical to see what that yield was. So starting with 50.0 grams of Fe2O3. And again, we're going to say this is A and Fe is B. So we're starting from grams of A, we're going to go to grams of B as our first step of this reaction. Roadmap says if I going to do that, the first thing I need to do is go to moles of A using our molar mass. So if I look on the periodic table, the mass of Fe is 55.85. So I have 2 irons, 55.85 grams for each of those in a mole, plus 3 oxygens at 15.9994 for each of those. And I get a molar mass for Fe2O3 of 159.7 grams in a mole. So 159.7 grams of Fe2O3 in 1 mole of Fe2O3, and of course I put the grams of Fe2O3 on the bottom so I can cancel that out. Now I'm at moles of Fe2O3 or moles of A, and I want to get to moles of B. That's what the roadmap says I have to do. And in order to do that, I need to use the coefficients of that balanced equation. So we see that 1 mole of Fe2O3 reacts to form 2 moles of Fe. So moles of Fe2O3 cancel. I've got moles of Fe. And the last step, if I'm at moles of B and I want to get to grams of B, I need to use the molar mass of B. It's just Fe. So we find that 1 mole Fe on the periodic table, 55.85 grams of Fe. So that gets me to grams of the product. Now you might say, why am I doing this? They already told me the grams of Fe that I got. No, they told me how much I actually got. What we are doing is calculating how much I theoretically could have gotten or should have gotten based on starting with 50 grams of Fe2O3. So if we had 50.0 grams Fe2O3, divide by 159.7 grams of Fe2O3 in a mole of Fe2O3, multiply that by 2 moles of Fe in every 1 mole of Fe2O3, and then multiply that by 55.85 grams of Fe in a mole of Fe, and we see that we theoretically could have gotten 34.97 grams of Fe. Or in other words, that's the mass of Fe I actually put into the equation, and I only got this much Fe out. But here's what we theoretically could have gotten, 34.97 grams. Here's what we actually got, 32.7 grams. They gave us that. So to calculate the percentage yield, 32.7 divided by 34.97, that gives us a fraction of 0.935. We just multiply that by 100 to make it a percent, 93.5%. Last question is the same type of thing we've been doing, except now in a multiple choice format, which is of course what you're going to see in an exam type setting. So here we have 2 H2S plus SO2 goes to form 2 H2O plus 3S. And they're telling us that if we've got 17 grams of H2S, we've got plenty of SO2, they want to know how much sulfur can be made, how many grams of sulfur. So again, we're going to say A is H2S, B is S. We're starting at grams of A. We want to go to grams of B. Using my roadmap, we're going to first convert between grams of H2S and moles of H2S. So from 17 grams H2S, we look on our periodic table, sulfur is 32.07 grams per mole. So we have 1 sulfur, 32.07, plus 2 hydrogens, that's 2 at 1.0079, gives me a molar mass of H2S of 34.1 grams in a mole. So I'm going to put that on the bottom. So my grams of H2S will cancel. Next, once I have moles of A, I need to convert to moles of B, and I'm going to use the coefficients of the balanced equation for that. So we see every 2 moles of H2S react to form 3 moles of sulfur, according to the equation as written. I put the 2 moles of H2S on the bottom, so those cancel. And finally, I'm going to use the molar mass of the sulfur to calculate grams of sulfur. So that's 32.07 grams of sulfur in 1 mole of sulfur. Moles of sulfur cancel. And then I plug this in and see that 17 grams of H2S divided by 34.1 grams of H2S in a mole of H2S multiplied by 3 moles of S in every divided by 2 moles of H2S. Multiply that by 32.07 grams of S in a mole of S, and I get 23.98 grams of S, which rounds to 24, right there. All right, I hope this was helpful, guys. Have a great day.